Hello class, for today's discussion here in Mechanics of Deformable Bodies, this will be the fourth and last installment of our discussion about the fundamental concept of strain and deformation. Okay, so we are going to discuss here and solve statically indeterminate members using compatibility equations, and we are going to compute thermal deformation and stress on a body due to change in temperature. So let's start our discussion now. Okay, so we are now going to discuss compatibility equation. So this is the solution for solving statically indeterminate members. Okay, so what are statically indeterminate members? Okay, so if the equilibrium equations are sufficient to calculate all the forces, including support reactions, that act on a body, these forces are said to be statically determinate. Now, in statically determinate problems, the number of unknown forces is always equal to the number of independent equilibrium equations. So, if you can remember class, in your statics of rigid bodies or engineering mechanics, you learn about different force systems, right? No, for every force system, there is a corresponding maximum number of unknowns that we can solve in equilibrium. Um, let's say for concurrent force system in equilibrium. Okay, so the number of unknowns that we can solve are two are no unknown forces, because we can only generate two equilibrium equations. Same with parallel force system in equilibrium, we can only generate two independent equilibrium equations. So we can only solve maximum of two unknown forces. No, and also for non-concurrent force system, the maximum number of unknowns is three. No, since we can generate three independent equilibrium equations. Okay, so here class, if the number of unknown forces exceeds the number of independent equilibrium equations, the problem is said to be statically indeterminate. Okay, and for this type of problem, for this statically indeterminate problems, what we're going to use, to solve that, or to generate another equation, okay, is by generating compatibility equation. Okay, so let's say in a force system, you have two unknowns, and you can only generate, let's say, one equation, one equilibrium, independent equilibrium equation. No, so to solve for the two unknowns, you have to generate another equation. Okay, and that another equation, is the compatibility equation. Okay, so let's say here, class, consider the bar shown in the figure. Now, in this figure, we have this bar. This is fixed supported at both of its ends. So this is fixed supported at point A or end A. And at this end, this is fixed supported at point B. Okay, so from the free body diagram, of this member, okay, so let's say we draw its free body diagram. So there will be a reaction here at point A and a reaction here at point B, since this is fixed supported. No, so drawing its free body diagram, so this will be its free body diagram of this member. No, so there will be a reaction here, at point A, and there will also be a reaction here at point B. So these reactions are unknown. Okay, so if we are going to generate the equilibrium equation from this free body diagram, so summing of forces vertical here. Okay, so the equation will be FB plus FA minus P is equal to 0. Okay, so this is the only independent equilibrium equation that we can generate from this free body diagram. Now, even if we, let's say, take moment, at any point, within the line of action of these forces, so there will be no equation, because they will all pass through the center of moment. They will all be zero. And even if we take moment, at any point outside the line of action of these forces, okay, so the equation, okay, or the moment equation, okay, that we can generate will just be equivalent to this equation. Okay, so meaning to say, class, this is the only equation, no, that we can generate, no, and since that is the situation here, no, so this type of problem is actually called statically indeterminate. Okay, since the equilibrium equation, no, it's not sufficient to determine the two reactions on the bar. So even if we have the value for P, no, for force P, let's say this is known, no, there will still be two unknowns, no, and we only have one equation for this equilibrium equation. Okay, so for this type of problem, no, we are going to introduce compatibility equation. Okay. Okay, so now, how are we going to establish the compatibility equation? Okay, so in order to establish an additional equation needed for solution, it is necessary to consider how points on the bar displace. So we are going to analyze, no, the displacement or the deformation, okay, that will happen on a body. So specifically, an equation that specifies the conditions for displacement is referred to as a compatibility equation or kinematic condition. Okay, so because the source of the compatibility equations is displacements, these equations contain as unknowns either strains or deformations. Okay, we can, however, use Hooke's law to express the deformation measures in terms of stresses or forces. Okay, so we know that we have, in Hooke's law, now we have formulas for strains, no, in terms of stress. So that is actually stress over E, right? But also we can actually express strains also in terms of deformation, right? So strains is just equal to the deformation over the original length, right? And also for deformation, we can express this in terms of stresses or forces. For forces, no, we can express deformation as PL over AE, force P, yeah, PL over AE. And in terms of stresses, no, we can express that as sigma L, no, over E, since P over A is equal to sigma. Right? So from that, no, the equations of equilibrium and compatibility can then be solved for the unknown forces. Okay, so just to summarize, no, the procedure for solving statically indeterminate problems using compatibility equations. So the first thing that you have to do is draw the required free body diagrams. Okay, and you have to derive the equations of equilibrium. Okay, so that's the first thing that we have to do. How we have to generate the independent equilibrium equations from the free body diagram. Okay, and from that, no, the second step, we have to derive the compatibility equations. Okay, so to visualize the restrictions on deformation, it is often helpful to draw a sketch that exaggerates the magnitudes of the deformations. Okay? So here, class, no, we are going to analyze, no, the occurrence of the displacement or the deformation. Okay, so from that, we are going to derive the compatibility equation. Okay, and after we derive that, no, we are going to use Hooke's law to express the deformation or strains in the compatibility equations in terms of forces or stresses. So it depends, no, on what is being asked in the problem. So if you are being asked about the force, no, we can use the formulas here, no, that is expressed, no, in terms of forces, such as this, no, for deformation, this is PL over AE. This is expressed in terms of force P, no. But if the question is stresses, no, so we can actually express deformation also as stress, right? We can just say that P over A is sigma, so it can be sigma L over E, or we can also use this, no, the formula for strain in terms of stresses. So this is stress over E. We can actually express also a strain, no, in terms of deformation. So strain, we know that this is equal to delta, or the deformation over the original length, right? So we can use those formulas, no? Okay. So after that, no, after we derive the equilibrium equation, after we derive the compatibility equation and use Hooke's law, no, for that equation, we can now use these equations, no, to solve for the unknown forces. Okay. Okay, so let's start solving sample problem here. For sample problem number 1, consider the bar shown in the figure, which is fixed supported at both of its ends. Okay, so if P is 40 kilonewton, length AC is 600 millimeter, length CB, this is 800 millimeter, and the diameter of this bar is 12 millimeter, and its modulus of elasticity is 200 gigapascal. So determine the reactions at supports A and B. Okay, so for this problem, no, we know that we can only generate one independent equilibrium equation. Okay, so since there will be two unknowns here, no, so there will be an unknown reaction here at A and an unknown reaction here at point B. No, so we have to establish another equation, okay, to solve these two unknowns. Okay, so that equation will be the compatibility equation. Okay, so let's solve this problem. Okay, so for this problem, what we're going to solve here is the reaction at support A and B. Okay, so the first thing that we have to do, no, to solve this problem, we have to draw first, no, the free body diagram, okay, of this, of this given bar, no, fixed supported at both ends. So its free body diagram will be this figure. Okay, so since this is fixed supported, no, there will be a reaction here at A and a reaction here at B. No, so this will be our bar. Okay, and there will be a reaction here at point A, so we will name it as F sub A. Okay, and there will also be a reaction here at B, and let's say that this is F sub B. Okay, so from this free body diagram, okay, we can establish an equation, no? So in equilibrium, of course, this will be in equilibrium. Okay, so we can use summation of forces vertical here, no, to generate the equation. So this will be equal to 0, so positive for upward forces. Okay, so this will just be FB. So this is positive. FA, this will also be positive since they are both upwards, no? And then for the value of P, no? So the value of P here is given in the problem. So the value is 40 kilonewton. So expressing that in Newton, so this will be 40,000 Newton. And this will be negative since this is downward. And this will be equal to 0. So since this is in equilibrium. So this will be our equation 1. Okay, and this is the only equation, okay, that we can generate here, or the only independent equation that we can generate here. Okay, so we need to establish another equation, which will be the compatibility equation. Okay, so from here, now if we are going to analyze, no, the displacement that will happen here, or the deformation, no, there will the deformation actually here, no, since this is fixed supported, no, there will be no chance, no, that this bar will elongate or contract, no, since it is fixed supported at both ends. No, so we know that its displacement or deformation will be 0. Okay, but we know that from point A to point C, no, from point A to point C, we can solve for its deformation. Same with from point C to point B, there will also be a deformation, right? And the summation class, the summation of the deformation from A to C and deformation from C to B, that will just be equal to 0. Okay, so from that, we can say that, let's say for the deformation from A to C, no, as we can see here in the free body diagram, if you are going to solve the deformation from this point up to this point, no, so this will be the internal normal force that we need, no, to solve for the deformation. Okay, so this will actually cause this bar, no, from point A to point C to elongate, since the normal forces here are in tension. No? So it will elongate, this part will elongate. So let's say this will be positive here. So that's our assumption. Let's say, no, for this equation, positive for elongation. Now, for the deformation, no, from point C to point B, no, from point C to point B, let's say this is the free body diagram, no, to solve for the internal normal force, to know the deformation here from point C to point B. Okay, so this will be the internal normal force. Okay, and to solve for the deformation here, no, the deformation will be contraction, right? Since the forces here, class, no, this will cause this portion from point C to point B to contract. Okay, so here, no, the contraction will be negative. Okay, so if we solve this, no, the deformation from A to C and the deformation from B to C, no, delta A minus delta B, so this will be equal to 0. Since there will be no deformation here since they are fixed supported. So this will now be the compatibility equation. So this is now ano, no, in terms of deformation. Okay, so from here, we can use Hooke's law. Okay, to express this equation, okay, into terms, no, that or according to what is being asked in the problem. So in this case, the question here or what are being asked, no, in the problem are the reaction forces FA and FB. Okay, so here, no, the formula that we can use, class, no, we can express these deformations in terms of forces A and B, right? No, so we can use formula PL over AE. Okay, so let's say for the deformation, no, A, so that will be the deformation from point A to point C. So we will consider this. Okay, so class, the internal normal force here will be FA. Okay, that will be our P, no, PL over AE, and the length here will be LAC. Okay, so this is actually given, no, in the problem, length AC. Okay, over A, or the area here at AC, no, which will be the same din naman, no, with the area of length CB, no, minus the deformation of length CB, no, so let's say that is delta B, so this will also be PL over AE, so the corresponding P or the internal normal force here will be FB, okay, and its length will be LCB over AE. Okay, so the modulus of elasticity, no, for this bar, no, is given also in the problem, and this will be equal to 0. Okay, so substituting the given here, no, for length AC, that is 600 millimeter. For the area, so the diameter is given, so that will just be pi over 4 diameter squared. So that will be pi over 4, 12 squared. So we just have to be consistent here, class, how with the units. So if this is in millimeter, this should be also in millimeter. Times the modulus of elasticity. So the modulus of elasticity is 200 gigapascal. So let's be consistent with the units. Let's use megapascal here, class, no, so that it can become Newton over millimeter squared. Okay, so that our equations here or the terms in the equations here, class, will be expressed in Newton and millimeter, ha? Okay, minus for this, so FB, so that is unknown, times 800 millimeter, that is the length CB, over pi over 4, 12 millimeter squared. So this is the same area. Okay, and then times the modulus of elasticity, this is also the same. So this will be equated to 0. Okay, so simplifying this further, no, so this will be the value for this, no, so this is 0.00026526 FA, and for this, no, so this will be 0.000035368 FB, so this will be equal to 0. So we can now express FA in terms of FB. No, so this will now be our second equation. Okay, so solving equation 1, no, this equation 1 and this equation 2, okay, we can now solve for the unknowns. No, so from the equation 1, no, we can substitute the value of FA that we derived here, no. Okay, so we can substitute that. here, no? So this FA will become 1.3332 FB minus 40,000. So this should be in Newton, ha? We have to be consistent, class, in our unit. So this will be equal to 0. So here there will only be one unknown, so we can directly solve for FB. So solving for FB, no, we can input this in our calculator. Okay, so this is just 40,000. We transpose it on the other side over FB, no? So that will be 1 plus 1.33332. Okay, so again, the value here, class, for FB is 17,142.96 Newton, or it can also be 17.143 kilonewton. Okay, so this will now be the answer, no, for the reaction at B. Now, for the reaction at A, no, we can use this, no, and substitute that FB here to solve for FA. So solving for FA, this will just be 1.33332 times 17,000. 142.96. So the answer for this will be, okay, if we input that in our calculator, okay, 142.96. So this will be 22,857.05, no, or 04 Newton. Or it can also be 22.857 kilonewton. Okay, so this will now be the answers for this problem. Now, for sample problem number 2, the concrete post in the figure is reinforced actually with 4 symmetrically placed steel bars, each of cross-sectional area 900 millimeters squared. Okay, so compute the stress in each material when the 1,000 kilonewton axial load is applied. The moduli of elasticity are 200 gigapascal for steel and 14 gigapascal for concrete. Okay, so we have here, class, this concrete post. Okay, and this concrete post, no, so this is composed of this concrete, no, so the cross-sectional area for the concrete is 300 by 300. So we will subtract, class, the area of the steel here, no, to solve for the area of the concrete. Now, for the steel, no, for each steel here, we have 900 millimeters squared cross-sectional area. Okay, since there will be 4 steel here, class, so the area will be times 4. Okay, so from here, class, no, we are going to compute the stress in each material when this 1,000 kilonewton load is applied on this post. Okay, so let's solve this problem. Okay, so for this problem, we are asked to solve for the stress in each material. So in this case, the materials here are steel and concrete. Okay, so we are going to solve the stress in the steel and the stress in the concrete. Okay, so to do that, okay, to solve this, class, now we have to draw first the free body diagram. Now let's say we cut a section, no, through AA. No, so cutting that section and drawing that free body diagram. So this will now be the free body diagram, no, considering the upper part, no, of the, or the upper segment. Okay, so we have here the load 1,000 kilonewton, and then let's say for concrete, no, so the force, no, that represents, no, the concrete. Okay, so that will be a PCO. Okay, so this will be the force, no, okay, or the reaction force due to the concrete, no. Okay, so also for the steel, no, there will also be a reaction forces, no, in the steel, and let's say that those forces, no, it will be represented by PST. Okay, so the forces, no, here in this 4 steel bars, okay, let's say it is represented by force PST. Okay, so from here, class, no, we are going to generate, no, the equilibrium equation. Okay, so summing up forces vertical here. Okay, so all the forces, no, representing this 4 steel bars, so that will be PST. Okay, so that will be PST plus the force, no, that represents the concrete, so that will be PCO minus, no, the load here. This is downward, so this will be negative 1,000, and then we multiply it by 1,000, no, to make it Newton, okay, just to be consistent in our units here. So this is the only equation class, no, that we can generate, no, from the equilibrium of this free body diagram. Okay, so we have to generate another equation, no, since we have here two unknowns. So that another equation, that will be the compatibility equation. Okay, here pala class, no, we can express these forces, no, in terms of its stresses. Since the question here class are stress or stresses, no, in the steel and in concrete. So we will express force for steel and force for concrete, no, in their corresponding stresses. So using sigma is equal to P over A, no, so that's the formula for stress. So that for force, no, so that will just be sigma times A. So this will be sigma ST times area of steel plus the sigma or stress of CO times the area, okay, of the concrete. So that will be equal, now we just transpose this, so that will be equal to 1,000 times 10 raised to cube, no, or 1,000 Newton, no. So this will be our equation 1. So again, for the second equation, so that will come from the compatibility equation. So here class, no, what will happen here class, no, for the deformation of concrete and steel, okay, so plus what will happen is for the deformation to be compatible, the changes in the length of the steel rods and the concrete must be equal. Okay, so the deformation that will happen in the concrete, okay, and in the steel will be equal. So we can say that the deformation of the steel, no, so that will be equal to the deformation of the concrete. Okay, similarly, no, we can also express this in terms of strain. No, so this is just directly proportional to the deformation. So we can also say that the strain in the steel, that is equal to the strain in the concrete. Okay, so from this compatibility equation, we can use Hooke's law to express strain, no, in terms of what is being asked in the problem. So in the problem, so this is stress, no, so we can express strain, no, in terms of stress. So the formula for that from Hooke's law, no, so that will be this one, no, strain. This is actually equal to sigma over E. Right? So this will be the sigma for steel over modulus of elasticity of steel. So this will be equal to the sigma of concrete or stress in the concrete over modulus of elasticity of the concrete. Okay, so the modulus of elasticity for steel and concrete, they are given in the problem. So we can just substitute them here. No? So solving for the stress in the steel, no, in terms of the stress in the concrete, no, substituting EST and ECO, that is 200,000 megapascal over 14,000 megapascal, no. So 200,000 divided by 14,000, that is 14.28571. So the stress in the steel, this is 14.28571 sigma CO. Okay, so this will serve as our next equation, no. Okay, so this equation, we can use this, okay, and the equation 1. Okay, this equation and this equation, no, we can use them, no, to solve for the unknown stresses. Okay, so here class, there is an area for steel and area for the concrete. So we can solve the cross-sectional areas for steel and concrete. So for the cross-sectional area of steel, no, so class, take note that we have here 4 steel bars. So each steel bar, the cross-sectional area is 900 millimeters squared, now as given in the problem. So that will be multiplied by 4. Okay, and this will be 3,600 millimeters squared. Now for the area of concrete, so the cross-sectional area here class, no, the dimensions are 300 and 300. Okay, so that will be the area, no, but we have to subtract, no, the area that is taken, no, by the, or consumed, no, by the steel, no. So we will subtract the area of the steel here, no, to solve for the exact area, or cross-sectional area of the concrete. So that will be 300 millimeter times 300 millimeter times the area of the steel, which is 3,600 millimeters squared. So the area of the concrete here, class, will be 86,400 millimeters squared. So we can now substitute this, no, these values to the areas here in equation 1. Okay, and we can also use this equation, no, and substitute it, no, in this equation 1. Okay, so from equation 1, so again, no, for steel, no, for the stress in steel, no, we can rewrite this as 14.28571 sigma CO, okay, times the area of the steel, which is 3,600, plus the stress in the concrete, okay, so that is unknown, and then the area of the concrete is 86,400. Okay, so this will be equal to 1,000 times 10 cube. Okay, so from here, we can see that there's only one unknown, which is sigma CO. So we can now solve for sigma CO here. So we can input this in our calculator. No? So this will just be 1,000 times 1,000 over, we can combine the two COs. Okay, so this will be 14.28571 times 36. Okay, plus 86,400. Okay, so the value for this class is 7.25539. No, so this will now be the stress in the concrete. Okay. So also for steel, since we already have the stress for concrete, we can just substitute this value to this equation to solve for the stress in steel. So solving for the stress in steel, this will just be 14.28571 times 7.25539. So this will just be 103.648 megapascal. So this will now be the stresses in each material. This is the stress for concrete and this is the stress for steel. So this will now be the answers for this problem. Okay, for number 3, the steel rod shown in the figure has a diameter of 10 millimeter. Okay, and it is fixed to the wall at A. Okay, and before it is loaded, there is a gap of 0.2 millimeter between the wall and the rod. So this is that gap. Okay, so before application of this load P, no, there is a gap of 0.2 millimeter here. Okay, so determine the reactions at A and B prime, no, if the rod is subjected to an axial force of P is equal to 20 kilonewton as shown. No, so neglect the size of the collar at C. So take modulus of elasticity for this steel rod as 200 gigapascal. So let's solve this problem. Okay, so for this problem, we are going to solve the reactions here at A and here at wall B prime. But take note, class, here, no, that this reaction at wall B prime, no, this will only take place, no, if this end B, if this will touch, no, this wall, no, that's the only time that there will be a reaction here at B prime. Okay, so class here initially, no, this end B, no, this doesn't touch this wall. Okay, so initially there will be no reaction here. Okay, but after the application of this load P, which is equal to 20 kilonewton, okay, so this will cause this bar to elongate, right? This will cause this bar to elongate, and this will cause this end B to touch this wall. Okay, so that will be our assumption. That that after application of this load P, this bar, okay, it will elongate and this end B will touch B prime. No, and if this B and B, no, this, if this touches this wall, okay, there will be a reaction here. Okay, so to solve this class, now we have to generate first, no, the equilibrium equation here from the free body diagram. So this will be the free body diagram, no, after the application of the 20 kilonewton force. Okay, so there will be a reaction here since our assumption here, class, is this NB will elongate, no, it so that it will touch the wall here at B prime. So there will be a reaction here. So that reaction is F sub B. Okay, so we can also check that assumption, class, no, in our computations here and in the answer. So we will know if our assumption is right or wrong depending on the answer. No, so in this case, class, no, we have to generate here the equilibrium equation. So there will only be one equilibrium equation here, no, independent equilibrium equation. So that will be summation of forces horizontal is equal to 0. So this will be negative FA minus FB plus this 20 kilonewton expressed in Newton. So this will be 20,000 Newton equals to 0. Okay, so our assumption here is positive for forces that are directed to the right, or directed to the right. Yeah. So here, class, no, so this will be our equation 1. Now, for our equation 2, okay, so we are going to use compatibility here. Okay, so again, class, this force P, no, this will cause point B, no, to move with no further displacement. Okay, this point B, no, it will move here at B prime, no, to this wall, no, with no further displacement. Okay, so therefore, the compatibility condition for the rod is, so what will happen here, class, the total elongation, no, or deformation caused by this 20 kilonewton force, that will be 0.20 millimeter. Okay, so the summation of the deformation from A to C and deformation from C to B, if we sum them up, that will be equal to 0.2 millimeter. Okay, so that will be our compatibility equation here, class. Okay, that the deformation A, or the delta A, which will be caused by the deformation here at length AC. So as we know, class, no, the deformation that will happen here, class, no, since if we draw the free body diagram of A to C here, class, no, there will be a reaction force FA here, and the internal normal force here will be tension, no. So this will cause this portion from A to C, okay, to elongate. So it will elongate. Okay, so that will be positive here. Okay, and now for this C to B, if you are going to draw its free body diagrams, so we know that there will be a reaction force here, right? So if we draw the free body diagram of CB, no, so let's just consider the right segment. So there will be a compressive internal normal force here. So this will cause this bar, no, to contract. So that will be negative here. Okay, so the deformation of AC minus deformation of CB, no, so that will be equal to 0.2 millimeter. Okay, so this will be our compatibility equation. Okay, and we are going to express this, no, in terms of forces, no, since the question here is reaction. So using Hooke's law, so this will be PL over AE, no, for delta, or for deformation. Okay, so for the total deformation, class, will just be equal to delta A minus delta B, where in delta A, that is FA times L length AC over AE, then minus the delta B. So the delta B here, class, is PL over AE, so that will be FB LCB over AE. So we will just substitute here, class, that this deformation, class, again, that is 0.2 millimeter. Okay, FA is unknown, and then the length AC is 400 millimeter over the area of AC, which is pi over 4 times 10 millimeter squared. So that is given in the problem. The diameter is 10 millimeter. And then the modulus of elasticity is 200 gigapascal. So that will be 200,000 megapascal, or Newton per millimeter squared. Okay, so also for this, no, so FB is unknown, the length CB is 800 millimeter, our area is pi over 4 diameter squared times modulus of elasticity, which is 200,000 megapascal. Okay, so from here, no, we can solve this further, no, so this term, so this will be 0.000025465 FA minus this term, This is 0.000050930 FB. Okay, so this will be our second equation. No? So using equation 2 and equation 1, we can now solve the two unknowns. Okay, so here, from equation 1, no, the value for FA class is negative FB plus 20,000. So this is in Newton, ha? Okay, so just to be consistent, okay, with our units. Okay, so we can substitute this FA, okay, to the FA here in equation 2. Okay, so substituting that, no, so what will happen here, class? No, 0.2 times 0.0000025,465 FA, which is negative FB, plus 20,000 minus 0.000050930 FB. So the unknown here is FB. No, so we can solve for FB here. No, so solving for FB. Okay, so you can input that in your calculator. Okay, to solve for FB. Okay, so I'll just input this. Okay, minus 0.000050930. Okay, so the answer for FB here, class, is 4,048.69 Newton, or it can also be 4.049 kilonewton, no? So this will now be the reaction at B. Okay, now for the reaction at A. Okay, so we can use the FB that we already solved here. Okay, and we can substitute this FB, no, to either here or here. But in this case, let's just substitute here, no. Okay, so FA will just be equal to negative FB, which is that will be negative 4,048.69 plus 20,000. So this will be 15,951.31 Newton. So this can also be 15.951 kilonewton. Okay, so this will now be the answer. So here, class, no, if we are going to analyze our answers, no, since the answer here, class, is positive, no, so indeed, and B contacts the wall at B as originally assumed. Okay, so our assumption here, class, is correct that this force P, no, it will cause this end B, no, to touch this wall. No, so since our answers are positive. But class, take note here, class, that if our answers here are negative, okay, so the problem would be statically determinate. That means that this end B, it doesn't touch B prime or the wall, no, even after application of this force P. Okay, so in that case, no, the problem will just be statically determinate since there will be no reaction here at end B. No, so we can just solve for FA as 20 kilonewton, no, and the reaction here at point B will just be 0. So take note of that, class. So this will now be the answers for this problem. Let's now proceed to sample problem number 4. The three A36 steel bars shown in the figure are pin connected to a rigid member. Okay, so this member, class, no, this is a rigid member. So meaning to say it will not deform, no, this bar. Okay, so if the applied load on the member is 15 kilonewton, so this is that applied load, no. So determine the force developed in each bar. So we have here bar AB, bar CD, and bar EF. Okay, so bars AB and EF each have a cross-sectional area of 50 millimeters squared, and bar CD has a cross-sectional area of 30 millimeters squared. So what will happen here, class, is that this 50 kilonewton load, no, it will cause, no, these members, okay, so it will cause these members, okay, to be stressed. No, so it will be stressed, no, upon application of this load. So these bars, no, bar AB, bar CD, bar EF, they will also have strains. No, so they will experience deformations, no, upon application of this 15 kilonewton force. So again, class, this member, no, this member AE, no, this will not deform, ha. Okay, so the bars here that will deform will be A, B, C, D, and E, F. Since this member, class, this is rigid, ha. Okay, but it will be ano rin, displaced. It will also be displaced. Okay, because of these bars. no, that holds this member. Okay, so class, we are going to determine here the force no developed in each bar. So let's solve this problem. Okay, so for this problem, we are going to solve for the force developed in member AB, member CD, and member EF. So the first thing that we have to do here, class, is to draw the free body diagram, no, to generate the equilibrium equation. So in this case, class, this will be the free body diagram. So this force will be for bar AB, this force will be for bar CD, and this force will be for uh, bar EF, no? Okay, so there will be a 15 kilonewton load here, class. No, so this is a parallel force system, class, right? So in this kind of parallel force system, we can generate two independent equations here. No, one summation of forces vertical, no, and one summation of moment at any point. So in this case, class, let's say for the summation of forces vertical is equal to 0, positive for upward forces, so this will just be FA plus FC plus FE minus 15,000, no? So this is expressed in Newton, ha? So this will be 15,000 and this will be equal to 0. So this will serve as our equation 1. Now, for our second equation, we can use summation of moment here. Now, let's say we take moment here at point A. So the moment here will be 15,000 times 0.2 meters. So that will be 200 millimeter, no? And then its rotation will be clockwise, no, about point A. And then for FC, so its rotation will be negative or counterclockwise, no? So that will be negative. So times its moment arm, which is 0.2 plus 0.2 meter. So that will be 0.4 meter. And that is 400, no, in millimeter. Okay, and also for FE, so this will also have a counterclockwise rotation. So this will be negative here also. So its moment arm will be 0.4 plus 0.4. So that will be 0.8 or 800 millimeter. So this will be equal to 0. So this will be our second equation. Plus, here, we have here two equations. But the thing here, class, we have three unknowns. Okay, so we have to generate another equation. Okay, to solve for the unknowns. Okay, so class, our another equation here, class, will be derived from its compatibility, no, or the compatibility equation, no. Okay, so we will analyze here, class, no, the deformation or the displacement that will happen here. So in this case, class, no, since the 15 kilonewton load is located here, no, so this will pull down, no, this bar. Okay, so meaning to say, class, no, the bar here, class, that will be stress, no, since this member AE, class, this will not deform. No, this will not deform. Okay, so meaning to say, upon application of this 15 kilonewton, this will be stress, this will be stress, this will be stress. Okay, but class, here, the bar here, class, that will have the largest displacement, no, will be this bar. Okay, since this is rigid, no? So this bar will remain as it is, na this is just a straight bar, no? This will not deform. So the largest displacement, class, will happen here since this is the nearest, no, to the applied load. And the farthest, no, this bar, no, this will experience the least stress. So we can illustrate, no, the deformation or the displacement, no, that will happen here, no, in this system. So in this case, no, this bar, okay, member AE, this will be pulled down, no, by 15 kilonewton. So what will happen, class, no, this bar will be displaced this way, right? It will be, upon application of this load, it will be displaced this way. Okay, so that displacement, class, no, that is illustrated here. No, so this is the original position, class, of point A, point C, and point E. But upon application of this load, no, this point A, it will be displaced to point A prime. This point C will be displaced to point C prime, and this point E will be displaced to point E prime. Okay, so again, class, the bar, class, upon application of the 15 kilonewton load, it will be displaced this way, right? Okay, so this displacement, Okay, so this will be, no, or this will represent, no, the deformation, okay, that will happen, no, in bar AB. And this displacement, this represents the deformation that will happen here at member CD. And also for this displacement, no, this will represent the deformation that will happen here in this bar EF. Okay? So class, from here, no, we can use proportion, no, from this triangle. So again, class, this displacement, this is the deformation of bar EF. Okay, so this is delta E. Okay, so projecting this delta E, no, um just for us to have this triangle. Okay, so this is delta E here. So from this point to this point, this is ano ha, this is displacement A. No, or that is the delta A, the deformation of bar AB. Okay, from A to A prime. Okay, so class, this side of the triangle, okay, since we know that this is delta E, no, as we projected this here, okay, so the value of the height of this triangle will be displacement of A minus displacement of E, right? This height of the triangle. Okay, and also class here, no, this ano ha, this deformation or this displacement, this represents the deformation of ano ha, bar CD. Okay, so this will be delta C. Okay, so from this triangle class, okay, from this triangle, okay, class, this ano pala, this height, no, from this point to this point. Okay, so this is the deformation or displacement of C minus the displacement of E. Okay, or the deformation of C minus deformation of E. This ano, this height. Okay, at this point of the triangle. Okay, so from here, class, no, we can use proportion. No, from this triangle. So again, this triangle, class, the height is delta A minus delta E, and this base, this is 0.4 plus 0.4, no? Okay, so from here, class, no, we can generate an equation using proportion. Okay, so here, class, delta A minus delta E, that is the height of the triangle, over the base of the triangle, which is 0.4 plus 0.4, that is 800 millimeter. That will also be equal, no, to this smaller triangle. No, so the height of the smaller triangle, class, that is delta C minus delta E over the base of that smaller triangle, which is 400 millimeter. Okay, so from here, class, we can simplify this further, no? So cross multiplying this 800 millimeter to the other side. So this will be the result, no? And solving, class, for delta A, no, so this will become for delta C, no, so delta C times 800 over 400, so that will be 2 delta C, and then delta E times 800 over 400, so that will be negative 2 delta E, and then we just transpose this, no, and it will become positive here. So combining this 2 delta E, so this will just become negative delta E. Okay, so this will now be the equation here. Delta A is equal to 2 delta C minus delta E. Okay, so this will now be the compatibility equation. Okay, and then using Hooke's law to express this, no, these deformations, no, in terms of what is being asked in the problem. So the in the problem, we are asked here for the force, no. So here, class, we are going to express this in terms of forces, no. So the formula here will be PL over AE, no, for deformations. So for the delta A, okay, so again, this delta A, this is the deformation ha for bar AB. So that will be PL over AE. So that will be the force A, okay, and the internal normal force FA, no, for bar AB. Then the length AB, and over the area for that bar times the modulus of elasticity, okay, equal to, okay, so for this delta C, okay, so this will also be PL over AE. That is the force here at ano, no, bar CD, which is FC. And then times the length of CD over ACD times E. Minus for delta E, so that will also be FE times the length over AE. Okay, so from here, class, no, we can substitute, no, given here, the given here. Okay, so here, length AB is 0.5 meter. Okay, LCD is actually 0.5 meter also. Same with FE, no? We can actually just cancel this length, no? Since both sides, no, they all have length, no, the same length. So it can just be canceled, no? But we can also, ano naman, we can also substitute those values here, no? And it will just be canceled, no? As you will see in the, simplification, no, of the equation. Anyway, for the area, no, all of this for bar AB, no, and bar in the no, in the problem, no, so the cross sectional area for AB and AE, no, they are both 50 millimeters squared. But for CD, no, the area given is 30, no, 30 millimeters squared. Okay, so we will just substitute that here. And then also, class, for the modulus of elasticity, no, the steel here is 836. No, so from the table, no, we know that the value of the modulus of elasticity for 836 steel, that is 200 gigapascal. Class, just memorize that, no, because 836 steel, that is actually frequently used, no, in all problems here in mechanics of deformable bodies. So memorize, class, that the modulus of elasticity for 836 steel, no, is 200 megapascal, ha. Okay. And also, class, okay, so we just substitute those values here, class. So FA times 500 millimeters, so that is the length, over the area, so that is given, and then modulus of elasticity equal to 2 times FC, that is unknown, times 500 over 30 millimeters squared times 200,000 megapascal. Okay, for modulus of elasticity minus FE, this is unknown, times the length of EF, that is 500 millimeter, over the area, 50 millimeter squared, times the modulus of elasticity. So from here, class, we can simplify this. Okay, so solving for this term, no, 500 over this. So this will be 0.00005 FA. So you can input that in your calculator. So this will be equal to, for this term, so this will be 0.000166667 FC, no? And for this term, so this will be 0.00005 FE, no? Okay, so from here, class, no, this can be the third equation. Okay, so solving for FA here, class, so just divide both sides by 0.00005, no? So we can solve for FA. So this will become 3.3334 FC minus FE. Okay, and this will now be our third equation. Okay, so here, class, we already have three equations. This equation 1, this equation 2, and this equation 3. Okay, so we can use this equations, class, okay, to solve for the three unknowns FA, FC, and FE. So we are going to solve these three equations simultaneously. Okay, so class, from equation 1 and equation 3. Okay, so this is the equation 1, right? And equation 3, that is actually FA is equal to 3.3334 FC minus FE. So we can just substitute that, no, here in this FA. So this will become 3.3334 FC minus FE plus FC plus FE minus 15,000 is equal to 0. Actually here, class, FE, this negative FE and positive FE, it will be cancelled. No, so we can directly solve for FC. So solving for FC here, this will just be 15,000 over 4.3334 FC. So this became 4.3334 FC because we combined this FC and this FC. So this will be 3.3334 plus FC plus 1 FC. So that will be 4.3334 FC. So solving for FC, this will be 15,000 divided by 4.3334. No, so you can input that in your calculator. Okay, so the answer for this is 3,461.49 Newton. Okay, so this is actually the answer already for the force, no, in bar CD. Okay, now, using this FC, no, from equation 2, we can substitute this, no, to the FC here to solve for FE. So this will become 15,000 times 200 millimeter minus 3,461.49 Newton, that is the value of FC, times 400 millimeter minus FE times 800 millimeter. So solving for FE here, class, so this will give you 2,019.255 Newton. So this will be the answer, no, for the force in member EF. Now, for the remaining unknown, which is FA, no, from equation 3, no, we can use equation 3 and substitute the value of FC. Okay, so FA here will become um, 9,519.28 Newton. So this will now be the answers, class, for this problem. FA is equal to 9,519.28 Newton. FC is equal to 3,461.49 Newton. And FE is equal to 2,019.255 Newton. Okay, so let's proceed now to our discussion about thermal deformation. A change in temperature can cause a body to change its dimensions. Generally, if the temperature increases, the body will expand, whereas if the temperature decreases, it will contract. Okay, so let's say we expose a material, no, to a changing temperature. Let's say we expose a material to wherein the temperature increases or the temperature becomes hotter. Now, so what will happen to the material is it will expand since the temperature increases, since the temperature becomes hotter. Okay, so the material will expand. Okay, on the other hand, if that material is exposed to a changing temperature where the temperature decreases or the temperature becomes cooler, okay, so what will happen to the material is it will contract. Okay, so ordinarily, this expansion or contraction is linearly related to the temperature increase or decrease that occurs. So if this is the case and the material is homogeneous and isotropic, it has been found from experiment that the displacement of a member having a length L can be calculated using the formula delta T is equal to alpha times L times increment of T. So in this case, class, this delta T, this is the algebraic change in the length of the member. Okay, so this is the change in the length of the member due to the change in temperature. Okay, or this is simply the thermal deformation. Okay, and alpha here, this is a property of the material referred to as the linear coefficient of thermal expansion. So the units measure strain per degree of temperature. So the units for this alpha, it can be either 1 per degree Fahrenheit in the English system and 1 per degree Celsius or 1 per Kelvin in the SI system. Okay, so that is the unit for alpha. And plus this alpha or linear coefficient of thermal expansion, this can be found, no, in the table of the mechanical properties of some materials that I've included in our course material. Okay, so if this is not given in the problem, no, we can refer to that table, no, for the corresponding linear coefficient of thermal expansion for a certain material. Okay, so the delta T or the increment T here, class, no? So this increment T or capital delta T, no? So this is the algebraic change in temperature of the member. Okay, so this is the computed as the final temperature minus the initial temperature. Okay, so for increase in temperature, of course, the final temperature will be higher. No, if we subtract that to the initial temperature, it will give us a positive temperature. No, so that means that that the temperature increase. No, so that means to say that the member or the material that or the body that we are considering here, it will expand because the temperature increase. On the other hand, if the value for the final temperature is less than the initial temperature, so this will be negative, right? And that will signify, no, or indicate that the material, no, will contract. Okay, since the temperature decreased. Okay. Also, class, for L here, the L here, class, this is the original length of the member being considered. Okay, so the change in length of a statically determinate member can easily be calculated using delta t is equal to alpha L times change in t, since the member is free to expand or contract when it undergoes a temperature change. However, if in a statically indeterminate member, these thermal displacements will be constrained by the supports. Okay, thereby producing thermal stresses that must be considered in design. Okay, consequently, the analysis of thermal stresses follows the same principles that we use. Okay, so this is for statically indeterminate members. Okay, if we are going to consider thermal stresses in the computation, no, we are just going to follow the same principle. We are going to uh, establish the equilibrium equation, the compatibility equation, and we are going to use Hooke's law. So the only difference here is that we must now include thermal expansion in the analysis of deformation. Okay, so we are going to include this thermal expansion. Okay, so also class, no, you can take note of this conversion, no. Okay, so let's say the given in the problem, no, let's say for alpha, so let's say that is in per degree Fahrenheit, and the given temperature is in Celsius. So we should know how to convert these temperatures, ha. So these are the conversions for from degree Celsius to, or from degree Fahrenheit to Celsius, from degree Celsius to Fahrenheit, and from degree Celsius to Kelvin. So we can use this, ha. Okay. Okay, now for the procedure for deriving compatibility equations here in thermal deformations, no, for statically indeterminate members. So the first step is to remove the constraints, no, that prevent the thermal deformation to occur freely. This procedure is sometimes referred to as relaxing the supports. Okay, and you have to show the thermal deformation on a sketch using an exaggerated scale. So you're going to show, no, if the thermal deformation is contraction or expansion, no, depending on the change in the temperature. Okay, so after that, no, we will apply the forces that are necessary to restore the specified conditions of constraint. No, so this is the reaction force, okay, provided by the support. Okay, so we are going to restore that, okay, and add the deformation caused by that reaction force, no, to the sketch that was drawn in the previous step. So draw the magnitudes of the deformation so that they are compatible with the geometric constraint. So we are going to draw here, class, let's say if the deformation that will be caused by that reaction force is elongation, so we will indicate that it is elongation. If it's contraction, we will indicate that it is contraction. Okay, and after that, class, by inspection of the sketch, write the relationships between the thermal deformations due to the constraint forces. Okay, so that's how we can derive the compatibility equations here. Okay. Okay, so let's solve sample problem number 1. The horizontal steel rod, 2.5 meter long and 1,200 millimeters squared in cross-sectional area, is secured between two walls as shown in the figure. Okay, so this is the horizontal steel rod. So this is 2.5 meter in diameter. Okay, and this is 120 millimeters squared in cross-sectional area. Okay, so class, this steel rod, no, if this is stress-free, no, at 20 degrees Celsius, compute the stress when the temperature has dropped to negative 20 degrees Celsius. Use alpha is equal to 11.7 times 10 raised to negative 6 per degree Celsius, and for modulus of elasticity, this is 200 gigapascal. So we are going to assume here, class, that the walls do not move. Okay, and for the second assumption, the walls move together a distance of 0.5 meter. Okay, so we are going to to compute the stress. Okay, for the first one, for the first condition or assumption, stress when the walls do not move, and for the second one, the stress if the walls move together a distance of delta is equal to 0.5 millimeter. Okay, so let's start solving this problem. Okay, so for this problem, no, we are going to determine the stress, no, into conditions. Now, for the first one, our assumption is the walls will not move. Okay, so we are going to determine the stress assuming that the walls do not move. Okay, for the second condition, we are going to solve for the stress assuming that the walls move together at distance of 0.5 millimeter. Okay, so class, for the first assumption, okay, so we are going to solve for its stress. Okay, so class, take note that initially, no, at 20 degrees Celsius, okay, so this member, this is stress-free. Okay, so there is no stress here, no, initially at that temperature. But because the temperature decrease, no, to -20 degrees Celsius, no, so because of that decrease in temperature, change in temperature, no, so this member, no, it will be stressed. Okay, it will be stressed since um, the ends of this member, they are both fixed, no? So it will have no freedom, okay, to expand or to contract because it is restrained at both ends. Okay, so it will be stressed, no, due to the change in temperature. So here, class, uh, since this is fixed supported at both ends, though it will be stressed, okay, so the deformation here will just be 0, since the assumption here is the walls will not move. Okay, since the wall will not move, no, so meaning to say the deformation will be 0, but it will be stressed. Okay, so analyzing that, class, no, we are going to um, establish the compatibility equation. So to generate the compatibility equation, no, as given in the steps, no, in the previous slides, no. So the first step is if this is ano, no, restricted or restrained, no, if the member is restrained to expand or to contract, no, what we're going to do is remove, no, the one of the supports at its ends, no, so that it can freely expand or contract. Okay, so we are going to show that here. Okay, so in this free body diagram, okay, as you can see here, class, we remove here this support, okay, this fixed support. So after we remove that support, no, so this member now, no, it will be free to contract or expand. But in this case, the temperature change here, class, is decreasing. So meaning to say the member will contract. Okay, so the member will contract, so the deformation for this will be contraction, and we will name that as delta T. Okay, so class, the next step here is that we have to restore the restraint here, no? Okay, or the force, no, that causes the restriction. So in this case, class, since this is fixed supported here, no, this deformation, no, it will be prevented because it is supported here. No, so to indicate, no, that this restriction, no, provided by this support, no, we will draw here, class, no, the reaction force, no, that will cause that restriction, and that is force P. Okay, so this will ano, no, this will maintain, no, the length of this member. Okay, so if the temperature change, it will cause the member to contract, no. So this restriction, no, the direction of this reaction force, it should be to ano, no, to elongate, just to oppose, no, this contraction caused by the change in temperature. Okay, so this reaction force P, no, provided by this support, no, so the deformation that it will cause the this member, no, to occur, no, it will be elongation. Okay, so the deformation due to this reaction force P will be delta P. Okay, so take note, class, that the walls do not move. So the deformation will be 0. Okay, so the summation of this deformation and deformation, they should be equal to 0. Okay, so meaning to say, no, the deformation due to the change in temperature, it should be equal to the deformation caused by this reaction force P. Okay, so we will say that the compatibility equation here will be delta T is equal to delta P. Okay, so the deformation due to the change in temperature, that will be equal to the deformation due to this reaction force P. Okay, okay, so from here, class, no, so this is already delta T is equal to delta P. So using Hooke's law, okay, so we are asked here for, for stress. Okay, we are asked here to solve for stress. Okay, so we have to express these deformations, no, in terms of stress. No, so for that deformation due to the change in temperature, okay, we have a formula for that. No, so that is actually alpha change in T times L, right? So this is the formula for actual thermal deformation. Okay, equal to, so this is the deformation due to this reaction force P. Okay, so this will be PL over AE, but we can express P over A as sigma, no, since that is the item that we are solving here, stress, no. So we will express P over A as sigma, so this will become sigma L over E, no. Okay, so from here we can now substitute, no, the data here. So for alpha, it is given in the problem. The temperature, that will just be, or the change in temperature, that will just be the final minus initial temperature. So the final is 20 degrees, negative, no? Negative 20 degrees Celsius. And the initial is 20 degrees Celsius. Okay, and the length here is 2,500 millimeter, no? If it's expressed in millimeter. So this will be equal to sigma. Okay, so this sigma, this will be the stress. Okay, so that will be the thermal stress. Okay, and then times L. So the L here, class, is the length pa rin, no? And then E is the modulus of elasticity. So this is also given, no, in the problem. So substituting the data, the values of alpha. So the alpha is 11.7 times 10 raised to negative 6 per degree Celsius. So the temperature, final minus initial. So if the unit here, class, have for alpha is per degree Celsius, so the temperature here should be degree Celsius also, ha. But since the given is already in degree Celsius naman, so we will just directly substitute them here. So final temperature, negative 20 degrees Celsius minus initial, which is 20 degrees Celsius. And then times length, which is 2,500 millimeter, equal to the sigma times 2,500 millimeter over the modulus of elasticity, 200,000 megapascal. So here, class, no, we can directly solve for sigma since that is only the unknown. No, so solving here for sigma, as you can see here, class, the temperature here, class, no, this will become negative 20 minus 20, so that will be negative 40. So this indicates, class, that the temperature decrease, and meaning to say, no, because of that decrease in temperature, no, it will cause a compressive stress, no, compressive stress to the member. So this stress, class, no, as you can see here, this is negative. This is negative 93.6 megapascal. So this is a compressive stress, no. This negative sign indicates that this is a compressive stress. Okay, so this will now be the stress, that we are solving here in number 1. Now for number 2, the assumption here now is that the walls will move together at distance of 0.5 millimeter. Okay, so class, what will happen here, class? This wall, no, this wall will move due to the contraction, due to the change in temperature. It will contract. It will contract due to the change in temperature with a distance of 0.5 millimeter. Okay, so from here, class, we will say here, class, that this 0.5 millimeter, this will be the deformation that will happen to this member. Okay, so here, class, no, we are going to generate the compatibility equation here. Okay, so class, what will happen here? The wall will move, so because the member will contract. Okay, so class, the movement here or the displacement will be 0.5 millimeter. So that means to say that the thermal deformation, okay, even if it's fixed, no, at both ends, the compression or the contraction caused by the thermal deformation, no, that will govern since it will contract. Okay, so meaning to say, class, no, let's say for the step, no, for the procedure here, class, we are going to detach, no, one of its ends, no, so that the member can freely expand or contract. So in this case, it will contract. So this contraction, class, the deformation here will be compression. So that will be delta T. Okay, and then class, because this is ano nga, fixed supported here, now we are going to restore the reaction force provided by this support. So that will be force P. So this force P, it will cause deformation also, right? And that deformation will be elongation. Okay, so class, this elongation, no, this force P, it will not be enough, no, to oppose, no, the deformation due to the change in temperature. That's why it will move 0.5 millimeter. So meaning to say, class, no, the deformation due to the change in temperature, that will be greater than the deformation due to the reaction force P. Okay, so establishing an equation here, class. So this will be delta T, okay, minus delta P. Okay, that will be equal to this displacement, which is 0.5 millimeter. Okay, so again, this is the class, ha, the deformation, ha, the total deformation due to the thermal expansion or contraction, no, thermal deformation, and the deformation due to this reaction force P. Ha. Okay, so here, class, no, we are going to apply Hooke's law. So we are going to solve for the stress. Okay, so we are going to express these deformations, delta, no, in terms of stress. But for delta T, we have formula for that. That is alpha, change in T times L minus for this delta P, this will be sigma L over E is equal to this given 0.5 millimeter. So substituting, class, the given here for alpha, this is 11.7 times 10 raised to negative 6 per degree Celsius. Okay, times the change in temperature. The final is negative 20 degrees Celsius minus the initial 20 degrees Celsius times the length, which is 2,500 millimeter. Minus, our sigma here is unknown, that is the stress, and then L is 2,500 millimeter over the modulus of elasticity, which is 200,000 megapascal. So this will be equal to the given displacement, which is 0.5 millimeter. Okay, so this 0.5 millimeter, class. Okay, so from here, class, the unknown is sigma. So solving for sigma here, now this will be negative 53.6 megapascal. So the negative sign here, class, indicates that this stress, no, is compressive stress. Okay, so the thermal stress here, class, is a compressive stress since the change in temperature is decreasing. No, so it will it will cause the material or the member to contract. Okay, so this will now be the answers for this problem. Okay, for sample problem number 2, the rigid beam shown in the figure is fixed to the top of the three posts made of A36 steel and 2014-T6 aluminum. So again, this rigid beam, no, so this is supported by these three posts. Okay, so these posts are made of steel. So this is A36 steel, and also this is A36 steel, and this aluminum, this is 2014-T6, no, aluminum. So the posts each have a length of 250 millimeter when no load is applied to the beam, and the temperature is initially this is 20 degrees Celsius. Determine the force supported by each post if the bar is subjected to a uniform distributed load of 100 kilonewton per meter and the temperature is raised to 80 degrees Celsius. Okay, so here, class, no, initially, okay, without the application of the load, no, so this is the position of the steel beam. okay, or the rigid beam, okay, the rigid beam, no, this is supported by this supports, no, upon application class, okay, of this load, which is 150 kilonewton per meter. So what will happen is that these supports will be compressed, right? It will be compressed. Okay, so meaning to say, this post, since it will be compressed, it will go down, right? It will be compressed. Okay, but class here, we have to include here, class, in our computation the change in temperature, because in the change of temperature class, no, so here from 20 degrees Celsius it became 80 degrees Celsius, so the temperature class here increased, right? So meaning to say that will cause the members, okay, that will cause this steel and aluminum, okay, it will cause them to elongate, right? But we are going to include that in our computation, no, the expansion caused by the increase in temperature, but we will also consider here, class, the compression, no, due to the applied load. Okay, so let's start solving this problem, class. Okay, so for this problem, we are going to solve the force, no, supported by each post. No, so we are going to solve the force here, provided by this steel support, and then for this aluminum support. Okay, so for our solution here, class, no, class here, we have to solve for the force here at steel and force here at the aluminum, no. Okay, so what will happen here? There will be two unknowns here, no, the force provided by the steel support and the force provided by the aluminum support, no. So class, let's generate first, no, the equilibrium equation, no, from the free body diagram. So drawing the free body diagram here, no. So for its equilibrium equation, we can sum of forces vertical is equal to 0, positive for upward forces. So this will just be 2 FST. So these are identical steels, ha? So this will be just FST plus FST. So that will be 2 FST plus FAL minus the applied load. So the applied load here, class, this is 150 kilonewton per meter. So if you are going to convert that, no, into its equivalent point load, 150, no, so that will be 150 times this is 300 plus 300, so that will be 600 millimeter. Okay, so that will be 150 kilonewton per meter times 0.6 meter. So that is the the length of this distributed load. So that will be 90 kilonewton. Okay, so that will be equivalent to 90 kilonewton. This distributed load, this is equivalent to this point load, 90 kilonewton. Okay, so this will become negative 90 expressed in Newton. So this will be 90,000, ha? And this will be equal to 0. Okay, so class, take note here that this is the only independent equilibrium equation that we can get, no, from this free body diagram. Even if we solve, let's say, for or take moment at any point here, class, it will just give us, no, the equivalent equation as this. So, meaning to say, class, this is the only independent equilibrium equation from this free body diagram. Okay, so from here, class, no, we are going to establish a compatibility equation. No, so from the compatibility equation, as we know, class, this member, no, this is rigid. Okay, so what will happen, class, no? Since the support here is symmetrical, right? There is steel here at the left and steel here at the right, and it has symmetrical dimensions then, or lengths. No, so meaning to say, no, the displacement here will just be level. Okay, it will just go down. It will just be compressed. Okay, this steel, aluminum, and steel, these two steels, okay, and this aluminum, their displacement will just be on level, no? Level lang sila, class. So, it will just be equal, no? The deformation for the aluminum and the deformation for the steel will just be equal. Okay, so let's say that the displacement for steel, it will go down. Now, it will just be equal to the displacement of the aluminum. So, it will also go down, this aluminum. Okay, so from here, class, no, what we're going to do here, class, is analyze no the deformation for steel and the deformation for the aluminum. Class, for the deformation of the steel. Okay, so let's say this is the no. So we can just consider one steel here since these are identical naman. No, these two steels are identical. So for the steel, okay, so class, there is a change in temperature here. The temperature increased. No, so meaning to say that the deformation due to that change in temperature, it will be elongation or expansion. So this illustration here, class, no, so this indicates that the um the steel will elongate due to the change in temperature. But also, class, this steel bar, no, this will also deform, it will be compressed, no, due to the load, no. So the deformation due to that load, class, will be this deformation. So this is the deformation, class, due to the force, no, the compressive force, okay, that it will support. This post will support. Okay. Okay. So, also here in the aluminum class, okay, so for aluminum class, no, it is easier to elongate, no, due to change in temperature, compared to steel. No, so in this case, class, no, the deformation due to the change in temperature will be this, no, and then the deformation due to the force that it will support, no, this post, no, so this will be this deformation. Okay, so from here, class, now, from here, we are going to establish an equation here for the deformation in steel. So, for the deformation in steel, class, no, so that will be the combination, no, or the summation of the deformation due to the load, applied load, and the deformation due to the change in temperature. Okay, so in this case, class, we just assume that for compression, no, so this is compression, this will be positive, and then for the thermal expansion, okay, or for the thermal deformation, this will be negative. So, class, our assumption, no, let's put it this way for our assumption, no. So, uh, the value, or the larger value, no, that we can uh, have, no, from our analysis. In this case, kasi, class, we assume that the compression deformation, no, that will give a larger value than the thermal expansion. Okay, so even if it will elongate due to the change in temperature, but because of the load, no, it will still go down, no, but it will just be class, it will just be lessened, no, that compression will just be lessened because of the thermal expansion. Okay, so in this case, class, so we will assume positive the deformation here that we assume that will have a larger value, which is the compression. Okay, so this will be negative delta ST due to the change in temperature plus the deformation of the steel due to the compressive load. Okay, so this is for the steel. Now for the aluminum, okay, so also this will be negative delta due to the due to the change in temperature, and then plus delta AL. This is due to the applied load, compressive load. Okay, so from here, class, no, this deformation, total deformation for steel and total deformation for the aluminum. Okay, so we are going to substitute this here in this equation. So in equation, in this delta ST, so this will become, okay, this will become negative delta ST, no, due to temperature, plus delta ST due to the applied load, no, and then equal to, for the deformation in the aluminum, so this will be the total deformation, negative delta AL due to the change in temperature plus delta AL due to the applied compressive load. Okay, so from here, class, no, we can rewrite this using Hooke's law. Okay, so for the deformation of the steel due to the change in temperature, so that will just be alpha change in T times L. Okay, plus the deformation due to the applied load, so that will just be FST, so that is the force in the steel, no? Okay, times L. So this is PL over AE lang, class, over A, okay, times E. Okay, and then equal to, okay, the next one is um, negative delta AL, no, due to the change in temperature. So that will just be alpha times change in T times L. Okay, minus, or plus rather, plus, so here, this is the, due to the applied load here, no, the reaction force here. So that will be PL over AE as well. Okay, so let's continue this, class. Okay, so from this equation, we are now going to substitute, no, the given in the problem. But in this case, class, the alpha, or the coefficient of thermal expansion, and the modulus of elasticity for steel and the aluminum, they are not given in the problem, right? But the type of steel and the type of aluminum was indicated in the problem. For steel, no, the type of steel is 836. No, so we can see, no, the values of alpha and modulus of elasticity of 836 steel from the table. Okay, so from the table, okay, for 836 steel, no, its alpha will be this value. So this value is 12 times 10 raised to negative 6 per degree Celsius. Okay, now for its modulus of elasticity, so this is the modulus of elasticity, this is 200 gigapascal. Now for the aluminum, so in the given, no, or in the problem, it is indicated that the aluminum is at 2,400, 2014 rather, 2014-T6 aluminum. So the value of its alpha will be 23 times 10 raised to negative 6 per degree Celsius. And its modulus of elasticity will be 73.1 gigapascal. Okay, so from this values, class, no, we can now substitute this here, no, in our equation. Okay, so for the alphas, this will be negative, no, times the alpha. The alpha is 12 times 10 raised to negative 6 per degree Celsius. No, this is for steel. Now for the temperature change, so that will be final 80 degrees Celsius minus initial 20 degrees Celsius times the length of the steel, that is 250 millimeter, plus FST here is unknown, class, and then 250 millimeter, that is the length of the steel, and then the area of the steel. So the given in the problem is the diameter, no, of the steel, which is 40 millimeter. So solving for the area, that will be pi over 4, 40 millimeter squared, times its modulus of elasticity, which is 200 gigapascal. So it is also equivalent to 200,000 megapascal. Okay, equals, then we have your negative, and then for the alpha of the aluminum, that is 23 times 10 raised to negative 6 per degree Celsius, times the change in temperature, that will be 80 degrees Celsius minus the initial 20 degrees Celsius, times the length of the aluminum, that is also 250 millimeter. Plus the FAL, so FAL is unknown, times 250 millimeter, that is the length of the aluminum, over pi over 4, 60. So the diameter given for the aluminum is 60 millimeter. So its area will be pi over 4, 60 millimeter squared, times the modulus of elasticity, which is 73.1 gigapascal. So that will also be equivalent to 73,100 megapascal. Okay, so from here, class, we can now simplify this. Okay, so for this term, now if we compute this, so this is negative 0.18. Okay, for this term, class, this is 0.00000009947 FST. For this, okay, so this is negative 0.345, and for this is 0.000001296 FAL. So from here, we can simplify this further. Now we can combine like terms. We can combine negative 0.18 and negative 0.345. So we can transpose this to the other side. So this will become negative 0.345 plus 0.18. That is equal to negative 0.165. Okay, so class, we are going to solve for FST here in terms of FAL. So we will divide both sides by this coefficient of FST. Okay, so the result here will become, so FST will be equal to negative 165,875.82 plus, okay, for this 1.21602 FAL. So we can now use this equation, okay, and the equation from equilibrium, no, that we generated, no. So since there will be two unknowns, so we have two equations here to solve those two unknowns. Okay, so solving equation 1 and equation 3 simultaneously. So from equation 1, this is the equation 1, right? Okay, so we can substitute this FST, no, to this, so that the only unknown here will be FAL. Okay, so solving for FAL here, class, it will give us 122,886.57 Newton. Okay, so this will now be the answer for the force, no, in the aluminum post. No? So now for the FST, or the force in the steel, so we can use this equation and just substitute the value that we solve for FAL. Okay, we just substitute this here. Okay, so the value of FST here will be negative 16,443.29 Newton. Okay, so class, this negative sign indicates, no, that our assumption for the force in the steel, no, is wrong. So our class, our assumption, no, from the figure B, no, our assumption for the steel is this, no. So this is in compression actually, right? And the aluminum is also in compression. So in this case, class, our assumption for FAL is correct. This is really in compression. But for steel, class, this means that it should be oppositely directed. Okay, it should be downward, no? This force in steel. No, so meaning to say this force in steel, this is in tension. Okay, so this is in tension. That's why it's negative here. Okay, so this will now be the answers, class, for this problem. So that concludes our discussion for this topic. I hope that you attain the learning outcome. So class, see you again on our next meeting. Okay, so keep safe, class. God bless. Bye-bye.